I guess we'll just wait a bit while everyone joins.
Yeah, sure. It would be a small subset of everyone anyway, so there's a bit more time for questions, I guess.
Yeah, I wasn't 100% sure on what we wanted to do, but I guess we'll continue with basically just answering questions, but a bit more specifically on the visualization, right?
Mm-hmm. Yeah, so the idea is, if there's anything specifically very deep in depth about things like Povray or maybe even PowerView.
I can try to show someone something if I need to with yeah. That would be no problem.
Mm-hmm. I haven't used Zoom much, but I presume there's a way that you can just allow people to join automatically without having to wait a waiting room.
Yeah. Well, it's 3 o'clock, I suppose. So.
Yeah.
Yeah. So hi everyone. It looks like most of everyone back pretty much. So I guess the aim for this session is just to focus a bit more on the visualization aspects of Vampire. So usage of VDC. You're very welcome to. Actually, let me see if I can bring up my chat because I can't see it yet. But yeah, how do I bring up the chat? Ah, there we go. You're very much welcome to ask any questions you have on either using VDC, its command line options, or how you might want to do specific things in, for example, Povray. I know Povray in particular, since it's its whole other thing, really, there's so many other options you can do with it. So maybe if you want to ask about how to make pictures look like really, really snazzy, if you'd like to make some publishable quality like photos of your simulations, then I can try and help you a little bit with that, give you some ideas for things you can change. Otherwise, in general, I'm very happy to help with any questions you have on visualization. So someone asked about making a GUI for VDC. I mean, I suppose for Vampire in general, we don't really have any intentions of making any GUIs, do we?
No. So it's a kind of interesting problem in a way. So if you look at for example, then yes, it has a GUI. Does that make it necessarily more productive? Not necessarily. It kind of lowers the barrier to entry a little bit because you can kind of click buttons to do things. But equally, having tried to play with them before, it's not the most intuitive piece of software in terms of getting your head around the GUI. So with Vampire, the main trick I think is getting to the command line, learning to run software that way, once you can do that, I think it's kind of more straightforward to kind of move things. Yeah. Agree with that. Okay.
Yeah, I mean, there's so many like side problems that come up with using a GUI for everything. I mean, to give you some sort of like of my personal experience, as soon as I got used to using a terminal for everything, then that's how I expected everything to be. Whereas beforehand, I would have used GUIs for everything. So to some degree, it's just a little bit of a paradigm shift of what you're used to. But yeah, there's a lot of trouble. But in terms of making one, of course, there's all the trouble with making sure it's platform independent and then keeping it updated. It's its own slight skill set, I suppose, to make a good one that works well. And then because for the visualization, for example, because there's the fact that we're integrating so many different programs together, it would also be a little bit difficult to get a GUI that interacts with those really nicely all the time. So in general, I mean, I personally quite like having the simple interface so that you can tweak everything exactly to how you need it. For the possible parse error, I cannot find colors.inc. That sounds more like a problem with how your POV has been installed.
There might be a POV includes.
Oh yeah.
Package in Ubuntu you might need. So, yes, there is. I'm surprised if it's not a dependency. But, so yeah, sudo apt get install povre-includes might grab the right color.inc files and so on and get them installed if it's not default. Yeah. Yeah. So in general, I think in Vampire, this visualization part of it is we found a big thing in Vampire that you need in many cases to actually inspect what you've kind of generated and try and understand the physics of what's going on behind the scenes. So be it if you have domain wall motion or you have some change of magnetic configuration or even just inspecting the structure that you generated. So there's kind of a big visual aspect to understanding atomistic simulations that maybe isn't so necessary with kind of other softwares, like for example, like Dynamics. So yeah, so since forever we supported Povre as a kind of nice piece of software to generate pretty pictures. The nice thing being that it's simple for someone like me to understand, where you create spheres or you create squares or cubes or whatever in a very simple way. So as a scientist, it was very easy to kind of get access to that basic kind of structure and generate something graphical. The downside is, of course, everything with Povre is very slow to render. So we did add support last year for PowerView, which is a kind of popular package for doing 3D viewing. Again, it has its own learning curve, but in general, then you have an interactive display with a number of atoms, and you can kind of rotate things. And I believe you can even run it on kind of cluster head nodes and things, have multiple cores to the processing. So it's quite a featureful way of looking at things. In general, in the group at York, we tend to use Povre almost exclusively, I think, for the kind of final images for publications.
Yeah.
It's slow, but you have almost complete control over everything that's kind of going on.
I suppose it might be worth explaining because, I mean, Povre isn't really a thing specific to what we do. And I suppose a lot of people might not actually know what the program really is. So in case you don't really know what the program is or why we're using it, I mean, Povray in general is just a ray tracing based image producing program. You provide it with a set of instructions on shapes and lighting effects to use, and it generates an image based on those. It's not really doing any physics or anything like that. It's producing an images using a ray tracing algorithm and the structures that you provide it with. So when you run VDC and tell it to make the inputs for Povray, what it's doing is it's making three files, a .pov file, a .inc file, and a .ini. If we leave out the ini for a second, which just has some default instructions for Povray for when you actually run it, the .pov file is a file that has information on where the camera should be, the background lighting for your image, and what exact lighting effects you'd like on your structures, you know, the spheres, the arrows, the blocks, whatever it may be. So that's just general settings for, you know, particular options and how everything looks. And then if you look at the .inc file, you'll see a whole list of lines, all the same, that just say spin M 1, 2, 3, etc. And that's a set of nine numbers, the first three of which are the positions. The second set of three are the spin directions, I think. And then the last set of three are the colors for those spins. So all in all, it's just a whole bunch of data where it's like, okay, take this object, put it here, render it. Take this object, put it here, render it, etc., etc. That's what Povray is doing. And so if you're trying to learn how to use Povray, there is of course a whole bunch of documentation if you want to like really get into it and tweak things around. But I think VDC produces a sort of very reasonable set of initial parameters for you to use. But so for example, when we actually want to make like really, really nice pictures that we want to put in a paper, we will spend a lot of time actually just tweaking these little parameters to get the right lighting, for example, or, you know, the right shine and everything. So it looks really, really, you know, crystal clear. And at that point, we want to make the images as big as possible, high resolution. So for example, if you're actually just trying to get some very quick pictures to see what's going on, if you look at my YouTube video, I suggest a few command-line parameters to use, like -W 1800 -H 1350. That's the resolution of the image. If you lower that, for example, to, I don't know, 800 by 600, it'll render the image much faster. It'll be lower resolution. It won't be as clear, but it's a nice way to just get going and make sure that what you're doing is just about right until you want to, you know, get that final really high resolution picture, basically. If you go and look at the Richard's overall vampire website, for example, you'll see many different examples of all sorts of stuff that Richard has, you know, handcrafted in Povray just by using blocks, spheres, rods, whatever it is, and rendered it in Povray to get some really, you know, stunning looking images. Yeah, Povray definitely has a bit of like, if you want to like really have a fine control on what you're doing, Povray does require a lot of initial like time investment to get it right. ParaView and VTK may very well be easier to get going with.
So there's a question actually, Daniel, here about is there a way to slice the output geometrically via Povray? So
yeah,
Daniel, I think maybe over to you. You influenced it, so
yeah. So I mentioned one in the video, which is the general option -- slice, which you can use to take. So let's say you have a block of your material. You can very easily cut it in half in any direction using that option. But there are a few different slices which you can make, which are used for different things. So there's, for example, slice void, which does the opposite of slice. Basically, it'll take out everything about the region that you've chosen. And then a few different versions that like tweak on what you're doing. But yeah, in general, if you're just running VDC, use Povray, or even for .xyz files, you can use the slice option just the same. So let's say you want to take half of your object along the x-axis, you do // 0.0, 0.5. So you're doing it from one end to halfway through. And then for the other four options, 0, 1, 0, 1. And that keeps everything in the Y and Z axis, basically.
So actually, so this is all in the VDC tool, which is kind of a middleware, if you like. It takes the raw output from Vampire and then turns it into something that you can then visualize and render. So often we found with big systems, maybe millions of spins, that rendering is far too slow. And if you get to the higher end of billions of spins, then even Power View will start choking on it. So the idea about these having slice options within VDC itself is that you can then pre-process your data to only look at, say, for example, 2D slice in a system just to see the configuration, or you can, again, look at sort of a subset to kind of make things at least manageable in terms of file sizes.
Yeah. It's a bit difficult to explain exactly command line options just by talking about them. So if you forget what I'm saying here, either refer back to the video where I've got some of them written down a bit more, or have a look at the manual. I've tried to explain what each one does and what you need to do for each one quite clearly there.
Although there is a technical way of doing it in Povray as well. It's not very efficient because you have these large files to process within Povray. And unfortunately, the parser in Povray is horrendously slow. So actually loading the data often takes much, much more time than actually rendering. But you can actually do programmatic statements, for example, if statements within Povray. So you can also do slicing within that if you want to. But it's sort of a bit worse than bash scripting. It's not very user-friendly.
The whole point of using slice when you run VDC is it takes your raw output, does the processing at that point, and then whatever you throw it to afterwards, whether it's a JMOL, a Povray, or whatever, it's got the reduced data set. So if you've got a very, very large amount of data that you're dealing with, let's say you've got a 100 by 100 by 100 nanometer cube, which for Vampire is, on the larger scale of things. And you actually just want to look at the surface configuration of the spins, for example, you can use the slice option, or slice void specifically in this case, to make it hollow on the inside. You can only choose to show the outer fraction of atoms around the system. And that way, when you generate an image, it'll look very similar, but you'll be processing a fraction of the total number of atoms in your system, which would make the time much more, much smaller.
Something else that's also maybe worth pointing out that may not be necessarily clear, it's not visualization per se, but also in the formats that Vampire supports in terms of the intermediate files. So by default, for readability, the configuration files are text files by nature. So they're more portable, you can move system to system. But if you're dealing with large systems with, say, hundreds of thousands or millions of spins, then there's also a binary output option, which unfortunately is not portable, but it is very fast. So VDC can read these binary files in the same way as it reads text files, but tens to hundreds of times faster than the text files. So again, they were listed in the manual, but it might be useful to point out that if you're within the same platform, so say everything's on Ubuntu or Linux or whatever, then you can output those binary files and process them in place.
This is an option that you'll have to use at the beginning in your input file, I assume, right?
That's right, yes. So in your input file under output, I think there's output format, and you can specify text or binary mode.
Yeah.
Yeah. Okay.
And actually, is that, I don't know, actually, is that detected automatically by VDC, or do you have to tell VDC that it's in binary?
So it's the purpose of separating in the meta files and data files. So the meta files are always text, but they then list all the data files that you then use within.
Yes, yeah.
So it's very, it's not very clever. It's simply clever in the way that it doesn't matter what format the data is in, because that's all contained in the meta file. So it kind of tells VDC what data files exist and where they exist and what their names are. So it kind of automates the process of what kind of data you have. So kind of any other questions? Okay, good.
So with regards to suppressing the text, you can always just pipe the text to dev null and it'll go away. If you turn off all the screen options, then nothing will get printed to terminal. Sorry, I think somebody's knocking at the door.
Okay.
Sorry. It'll suppress. If you send everything you pipe all the standard out to /dev/null on a Linux machine, that just essentially sends it to a socket. A file that isn't being listened to, and it'll get rid of it.
Andrea. Yeah, can't hear you. But yeah.
Restarting my laptop, sorry.
Okay.
No worries.
Okay.
So yeah, so I mean, by default, Vampire should not output an excessive amount of text. This is not by design. So usually only if you have the screen options and you're doing a time series do you produce lots of data. And if you run on a cluster, typically, then again, that kind of little output tends to go to the standard file. So hopefully it's not too terrible producing too much stuff.
Yeah, I was going to say, just make sure that you're not trying to use the screen as your main output for your data. The screen output is useful because it gives you a nice idea for smaller simulations what's going on. But for example, if you're submitting a large job to a cluster, you obviously want to make sure that all that output is being put into an output file that you can read at a later point.
Another point that might be interesting to kind of point out is that recently, I think last year, Vampire acquired support for non-magnetic atoms in the system. So by default in Povray, these are rendered as gray spheres. But again, within the Povray file, the .pov file, you can go in actually, if you want, you can remove them, or you can change different things with them. So it allows you to kind of accurately represent the crystal structures that you might be simulating, even if you include non-magnetic species. So you may or may not want that. But often if it's a sort of a bulk crystal, say like magnetite, and you have the oxygen sites in, it kind of makes sense to include that within the rendering. And so that option kind of exists there, and you can tweak how those atoms appear in the system. Okay. So in terms of any kind of other burning issues with visualization or getting data out, or
aside from that, I suppose you could, if there's anything that you'd really like to be able to output or visualize in a specific way, and you don't think that it's currently supported with the options that we have, then feel free to mention it. It's always nice to have new ideas for things if you think it might really help with a different kind of system, that kind of thing. Otherwise, I could mention a little bit. In terms of Gmon Raspberry, I suppose any XYZ file viewer that you use should be able to work with them, right? It's a very the format of the file is very standard. So anything that reads in .xyz file should work nicely.
also, I think, VMD case you can use. But I mean, there are lots of programs. Fast that you use, usually Mac, though it's fairly heavy. So if you have lots of atoms, you don't really want to use it.
Okay, so a question from Nikolai about, is there any difference in serial and parallel simulations? So great question. So yes, technically there can be. So by default, if you run a parallel simulation, then when you want to output a configuration file to disk, what it will do is it will collect all the data from all the processes onto one process and then write that onto disk. But Vampire also supports parallel output, so that actually you can have multiple output files per snapshot. So for example, in the extreme case, if I had, say, 10 processors, I could have it so that each processor outputs its own output file. So this is actually kind of a more kind of side question on parallel computing, but in principle, there's a kind of optimization of this problem, that you don't want one file because you're waiting for one processor to do all the I/O. You don't want multiple files because then you open too many files and you have to deal with them all. So there's an option in Vampire which is, I think, MPI nodes, which tells it how many output files to generate. So typically a good number is actually one output file per physical node, where then each node of, say, 20 or 40 processors outputs a single file from that node. But if you have maybe 10 nodes, then I would have 10 individual output files. So in terms of actually stringing all this together, the VDC tool will then read all of those files and deal with it. But it's a kind of, yeah, so in terms of how you process all of that, it doesn't matter to the end user in terms of VDC works as usual, but you'll have many, many more files, obviously, if you have more nodes in your simulation. So the default is always one, that you only end up with one file, but you can specify up to n processors number of files if you want. The format is the same, but the spin configuration, well, the atom positions on each process are sort of distributed anyway. So there's some difference in the ordering of how the data appears, essentially.
Yeah, I mean, regarding this last question, well, if you output on the screen, then your simulation will be generally slower. Now, if it is very fast,
Yeah, but that's just because of
what amount of
standard out? It's not because of extra calculation?
No, it's not extra calculation. It just writes twice.
It's just because writing to the screen is slow. If you pipe that screen to a file,
it's still slower than just running it.
Slightly slower, but it's significantly faster than just the screen.
Yeah, but
the slow thing about writing to the screen is that every write command has to flush its own buffer, because the screen's meant to be sort of like the standard out is real time. So it can't queue up things and output them at sensible times. It has to output it immediately, which slows everything down. Whereas writing to a file, it doesn't do that because it can buffer its output and things. Very little calculation is done twice though. I think there's occasionally a multiplication, like a scaling factor, that might be done twice, but the actual sort of main statistics are only calculated and stored once as you're going along. And then it just might be occasionally a scale is done twice. So if you're outputting a slightly different size of something, that is occasionally done in the actual output itself.
Yeah, I think in general, the thing to avoid is time series type simulations where you have, hundreds of thousands or millions or tens of millions of steps where you output every single time step. So unless your system is ginormous, then it will take a lot of performance hit because you're outputting so much data every single time step. So that's basically what you want to avoid. So if you're doing lots of time steps with very high resolution, then only output to the output file, not to screen. For things like Curie temperatures, where you have one update maybe every couple of minutes, it doesn't affect it at all. It's fine. It's only when you have lots and lots of output.
Also, regarding the first question, or at least the question about the parallel and serial output, it might be worth mentioning that the log file, though, so if you have your parallel simulation, your log file, as long as you output all in a single file, will be just for your head node, and so you will see just the information regarding that. Usually, I mean, more or less the information will be the same also on the other nodes. But for example, if you want to know how many atoms each core has, the log file, then you will see just the for one node only.
Yeah, the log file contains things like the decomposition shape and how many atoms are going where. And it should all be human readable, the log file. It's meant to be completely for humans. It's not meant to be passed by something afterwards.
Yeah, you just made me think of one of the things that I think that people should always keep in mind, which is in combination with the visualization. There's a lot of tools to just make sure what you're doing is correct or check that you haven't made some kind of small mistake. So always use the log files to make sure that if you're using multiple materials, they're in the right proportions. Okay, so this is a bit harder if you're doing it in parallel because, as they've just said, the log file doesn't quite tell you about the whole simulation. It only tells you one small portion. But let's say you're doing it in serial. You can use the log file to check if the materials you've used are in the right proportions. And similarly for visualization, definitely make sure you use the XYZ output if you're using any type of complicated structure to just check if your input's correct. Do one time step, output an image just to see your atoms and make sure that it's all looking good, because it's very easy to just, do something ever so slightly off, do a whole simulation that takes, a day or maybe a week, and then come back and realize that you could have fixed it just by looking at the input files in the first place, or by looking at, a simple visualization in the first place. To give you an example, for when I was doing a lot of core shell structures, I had the intention of doing a core shell that was half and half with two materials, and naively just thought, oh, okay, so I just need to have half of the radius as one material and half of the radius as another, and then realized later on that that's not how spheres work. If I just do that, then it'll be much less of the core and much, much more of the shell. So something like that can definitely give you, oh, wait, that's not quite right. The materials aren't in the right proportion.
Any other kind of questions that are still standing? Anything?
Or are people familiar with POVRay, or did they find any issue with it?
We've been getting a few questions here and there on a couple of common stuff. That's quite funny. I think probably at some point in the last few years, all of us have probably raised exactly the same question to each other, but they've slowly been buried in our heads because we fixed it and then just tried to forget about that problem ever happening so many years ago.
Written the script once,
Yeah.
and just run that over and over and over again. Never have to think about it again.
For example, someone had a problem with POVRay that was specific to the Mac. I had to use the -D option, and I'm pretty sure on my Mac at work I've made an alias to always use the -D option, but I've completely forgotten about that. So in my mind, I don't need to do that anymore.
The other thing that's also useful for POVRay in particular is the default is a grey background, so that almost all color spaces work correctly. And for publications, this is really not nice. And so it's often good to go in and put a white background in to the system. But the problem is that when you put an actual white environment around your kind of rendered object, it makes everything very bright or washed out. So it's often not the best. So what I actually tend to do is put a black background. So the background color in POVRay is set as black. And then I put a plane, which is actually white, underneath the system that you want to actually visualize. So it avoids the fact that you get kind of a white environment to your rendering, so that your colors are still nicely saturated, but you have a white background, which goes well, obviously, in a nice publication. So we often spend a lot of time finalizing the data and kind of doing these kind of little things, which are kind of a bit of a rabbit hole with Povray. You can kind of go down there and go to ridiculous ends to make things look pretty. But so basic things like not having grey backgrounds in publications is worth doing if you can.
I should probably mention some of the changes I made to VDC in the last couple of years to do with color maps, actually. So this is a general thing that I think probably everyone should be aware of if they're working with these kind of things. When you're visualizing your data and you're using particular color maps, especially where, for example, for a lot of our work, if you've got, if you're trying to use colors to distinguish spin directions, for example, or you're trying to use colors to distinguish things that are very similar to each other, you've got to be very careful on the colors that you're using because of human perception, basically. It's very easy for our eyes to be fooled by colors that, on a RGB scale, they might be equidistant, but actually to our eyes, they look exactly the same as somewhere else that looks completely different. So in general, under the hood, the color maps that I've implemented for Povray, the one that's used by default, and a few of the others, or all the other ones that are included, are made to be what's called perceptually uniform. So if you're trying to show spins that sort of change their orientation evenly and you're using a color map to show that, it should be showing exactly what you're seeing. So if you see a difference in colors between one part and the other and using different colors somewhere else, that should be exactly the same, change, basically. There's a lot of programs, like some even included by default in several really popular Python visualization tools or in GNUplot. A lot of color maps that are used by default have this flaw of not actually being perceptually uniform. So you'll see a lot of, very high quality published data of relief maps very often where the colors are actually very misleading and might make you think that there are bigger or smaller differences than there actually are. So in general, you've got a few options for color maps to, oh, nice. Yeah, exactly.
Yeah, so sorry, just to interject. So this is actually an example where the color map here, so this is a normal vortex simulation, than a vampire, but this is a kind of default color map which I put together, which is rather poor, and Daniel's done a much better job. And the configuration is actually spatially uniform, but these lines that you see are complete artifacts. They're not physical at all. So, in terms of biasing what you perceive here out of this data, the color map does have an important role. So I just wanted to kind of show a kind of concrete example of where things go very wrong, and how Daniel's new color maps avoid all this. These problems.
There is some give and take with it as well. So in general, I've tried to use color maps which are still quite vibrant, nice to look at, eye-catching. But unfortunately, usually the most vibrant color choices are also the ones that can be the most misleading. For example, very high contrast greens or very high contrast reds actually can be smeared out very easily by your eyes. So you might not actually see any difference in colors with very high contrast. But in general, the color maps that you can use with VDC and with Povray, some of them are still very much vibrant, still very nice to look at.
Obviously, the other thing to take into account when using color to display information is that a decent chunk of the population is colorblind. So if you can, you should include things like contours and things so that even if you are colorblind, you can still see graduated delineation. Obviously, there's a limit to what you can do with this. You can't put contour lines on a spin. That doesn't really make a great deal of sense, but it's always something to be aware of. And obviously, journals are quite often reproduced in black and white, which will do you no good if all of your data is portrayed in color.
Yeah. And in general, another thing you can do if you really want to choose specific colors, VDC, usage of Pulvery with VDC, there is an option to supply your own color map. If you're someone who really wants like a paper to be consistent in the colors that it uses, it's not too difficult to go out there and search for a color map, basically just a list of RGB values that use a consistent color set. And it's not too difficult. It's all explained in the manual how to use that with VDC, how to use your own color map. You basically just need to supply a file with a list of 255 colors, you know, R, G, and B values, and you're good to go, basically.
One point that just occurred to me is, for example, if you have a ferromagnetic system, or ferrimagnetic to be a bit more clear, or antiferromagnetic system, then obviously what you can have is local variations of the magnetization which are extremely rapid. So for example, if I'm looking at a configuration which I say is blue is up and red is down, if I have a ferromagnet and I visualize all the spins in this way, then it will just look purple, independent of the configuration. So there may be small variations in color, but you won't see the actual detail that you want. So often when it comes to at least two sublattice antiferromagnets and ferromagnets, you want to invert the color of one particular species compared to another. So I think, Daniel, we've implemented this feature within VDC as well, so that if you have two different materials, you can specify that the color is inverted. So that, for example, then you can see domain walls within the system much more easily than you would otherwise. Yeah,
so if you've got a system where you've got spins, which I've named the option --AFM for antiferromagnets, but if you've got any system where you have spins constantly right next to each other, which are opposite in direction or near opposite in direction, which will end up giving you an image that doesn't look very nice because you just have this mix of colors right next to each other that don't show anything very nicely. You can use this option --AFM and then whatever material you're looking at, and what it will do is it will swap the colors so that it's all even, but the actual spin orientation is preserved. So if you have a nice high resolution image, you can see that the arrows are pointing different ways, but the image is consistent. Like the colors show you the overall spin direction much more nicely. You can also use it to sort of cheat a little bit with different things. So for example, if you've got a system where there are particular spins that you'd really like to point out, then you could also use the AFM to actually make them different if you want them to stick out for some reason. All the parameter does is change the color, make it opposite to what it would normally be.
Not sure I understand the last question. Is it possible to visualize difference from the equilibrium?
Do you mean if, say, equilibrium is all pointing in one direction, to visualize an amount away from that direction? Is that what you mean? Oh, well, so for the average state, your color map, if you have either end of your color map being colors and the average state be the very middle. So I think, is the default still white in the middle?
Mm-hmm.
So the default for VDC has, I think, red on one end, blue on the other, and white in the middle. So
and it's cyclic.
It's cyclic. So you're viewing the amount of color is essentially how far away you are from the average. Assuming the system's average is at zero magnetization, I suppose. You could obviously have your color at negative magnetization and positive magnetization be the same, and then you'd have white at one end and the color at the other.
Yeah, so I think it's a slightly different question. So by default, if the equilibrium at zero temperature, say along Z, then sure, a visualization will show you the deviations of spins around that. Now, you can do a different vector, is that right, Daniel?
You can set whatever vector you want. Yep.
You specify any vector you like for the saturated color. So if you know the direction of the magnetization, you can look at deviations from that direction, which would do what you're sort of looking there. But it doesn't give you the Yeah, so I think the problem is that obviously if you have a different magnetization state, then it doesn't tell you how much more magnetized it is or less.
But that
Yeah.
would be a macroscopic visualization anyway, wouldn't it? Because an individual spin is not more or less magnetized, it's just how well aligned it is. So if you wanted to see how well aligned it was with then you'd be better off looking at the magnetization curve. It'd be more meaningful, I think. If you really care about a set of individual spins and how closely aligned they are, then you would just want to set your one end of your color gradient along the direction of where you think they're going to be aligned. So you could check all of the output files from your simulation to see which direction is the equilibrium direction, and then set that as the direction that Povray cares about, or VDC and Povray, and then you'd see the deviation from that direction. Eventually, the final, an equilibrium state would be all pointed along that direction. And then the way you would visualize that over time would be as probably some sort of animation or something. Yeah, that would be the way to do it if you wanted the atomistic, to see the change in atomistic level of the spins. If you want to see just the change in the total system or a section of the system, then the macroscopic statistics will give you a better idea of that. And there is a standard deviation built in that will tell you how much the magnetizations are varying over time, and then obviously your individual components will tell you how far you are from whatever you expect equilibrium to be, if you've got a field on it or something.
To answer instead the question about Weizhang, I would say, yeah, usually in such a case, a unit cell file, it would be probably the best. As Mara saying.
Sorry, I was just writing now.
Yeah, sorry.
So the idea with the unit cell files, you have more control on the type of your system you're generating. So you can have these very complex crystal structures. And also, as well, if you can parameterize your model from ab initio, then you can input directly the list of interaction in the unit cell file. So definitely for complex tasks, this is the way to do them.
Yes, the problem with the inbuilt DMI is it's more difficult to verify that it's doing the right thing. So it depends on, you have to get the cutoff radius correct for that and make sure that you only have the right number of nearest neighbors, for example. But as Mara says, in ab initio, you may have secondary contributions in the exchange tensor from next nearest neighbors or next nearest neighbors. So again, that may not be zero. So the inbuilt DMI is kind of a brute force. It's better than having to do simple systems by yourself or doing simple cubic, for example. You could actually have like an FCC structure with a more realistic kind of atomic DMI vectors. But it's still a close approximation to reality, I would say. The more complex the system, the better it is to verify that you have a unit cell file and does the right thing.
But for example, the inbuilt DMI would be very useful for alloys, where you have random positions of different types of atoms. So in that case, this is a very useful feature.
Okay, thank you. But my question is, you mentioned the alloy, but in the alloy, if in one unit cell, for every atom, it's not equal. It means number 1 between number 2 and the number 3 and number 4, they have different, for example, different exchange energy or different DMI interaction. So the built-in DMI will not work, right?
It can work, so you can specify different materials and kind of different interaction, but it's more safe to use the unit cell files.
Mm-hmm. Okay.
Yeah. So, for example, if you have 8 materials, you can do 1, 1, 1, 2, 1, 3, 1, 4. Yes. You could technically write it all out by hand. but it programmatically is much better, I think, if you can write a code and just
Do it.
get the code right. Well, I mean, excessively long material files.
Okay, in the UCF file, we can build a more real structure, I think, right?
Yes, that's right.
I think that also the idea is you can have more control, so it's easier to check that you're doing everything right.
Okay, thanks a lot.
But please bring this question back actually to the session probably tomorrow on unit cell files and Comeons and things. It's a good question to kind of bring up anyway.
I'm sorry, thank you.
Yeah. Okay. Also, hopefully for most people, the POV is working fine, or Power View. Again, I think if there's any kind of persistent questions, please do raise them at the Slack channel.
Yeah, definitely. If you have any problems, just put them in Slack. I've been trying to have a look at Slack every once in a while to make sure that if anyone has any problems, then I'll try to answer them and help with them. I mean, if you're really having trouble with it, don't worry. It's fine to just continually ask questions. But also you can have a look at the history just in case anyone's asked a similar question, because I know for sure many people are going to have similar questions with the same pitfalls with installing Pomfrey or using one particular thing or another. But don't worry about it. I'm very happy to just answer if you can't find it anywhere. Don't waste time trying to really look for it if you don't think it's there.
You're really quiet. I don't mean that visualization is completely trivial or.
I've done a brilliant job, haven't I?
Yeah. So, but
No topping your work, Dan. That's it.
What can I say?
Go home.
Yeah. As an aside, actually, Richard, is there any intention of including a pre-compiled version of the manual in the source?
That's really expensive in the Git repository, because I don't think Git is very good at telling the difference between. So if you change one character in the LaTeX and recompile it to a PDF, then Git won't recognize that it's one character different, and it'll want to include the whole file again. I think it depends on how it compiles the PDF and if you include fonts and things like that, but small changes lead to very big changes in size of the final repository.
Oh, okay, fair enough.
So
I think what we could do potentially is include the manual within the main releases. So we only update the actual PDF manual with every release, but include it in the repository.
there are also, can you not do like post clone hooks? So you could actually have it download from separate to the Git repository. I think I haven't played with those too much, but then you'd store the PDF outside of the repository, but it would still be pulled into the repository whenever somebody cloned down the thing. But I haven't looked at that too much. It might be a real pain, and it might be dependent on something like GitHub rather than, at the moment it's on GitHub, but if GitHub were to disappear, it could be moved. It's just a regular Git repository, but I don't know if that would. So might involve a little bit more work.
Yeah, make doc is a good plan actually. We should support that option.
Yeah, that would be pretty easy. It's not got that many in the way of dependencies, has it? It's
it's PDF LaTeX, so it's not.
Oh, okay, it's PDF, so it's
particular fonts as well. Although I think the Google fonts, so we could probably embed them in the repo as well.
Yeah, so we could do that. Make doc, make manual, something like that.
Yeah, that would be a good suggestion. Okay. unless there's any burning questions, we can kind of leave it there and let you guys go on. But yeah, give it a minute. Yeah. Well, thank you all very much for coming along, and yeah, I'll be in touch this evening with another playlist for YouTube and also everything else. So yeah, take care. Okay.
All right. Bye.
See you guys.
Bye.